next speaker is going to be talking about Scenic, a language for scenario specification and scene generation. His name is Daniel Fremont. And let me just mention, we had the Turing Award lectures yesterday. We heard a lot about deep learning. And one of the key things that we're trying to do with deep learning is generate training data. And so this talk is going to give us some insights about that.
Thanks, Ben. Set my timer. OK. Yeah, so as Ben said, I'm Daniel Fremont. And today I'm going to be telling you about this project we've been working on this language called Scenic. So the motivation for our work has been the increasing use in recent years of cyber-physical systems like robotics, self-driving cars, and so forth in safety-critical situations. So they're expected to operate with little or no human supervision, and things could be catastrophically wrong if they fail. So making such systems reliable is extremely difficult, and the primary reason for that is because of the complexity of their environments. So if you think about an autonomous vehicle, for example, a camera on the front might record an image like this. There's a lot going on in that image, and in an attempt to understand what's happening, extract some meaning from that, and make decisions, people are using machine learning to do this kind of perceptual task. So I'm going to describe the environment of an autonomous vehicle or any type of system at a higher level using what are called scenes. So I don't want to look at the pixel level information of what exactly is in this image, but a high level description. So what are the objects, what are their positions, orientations, and so forth. That I'm going to call a scene. And we'd really like to collect examples of real world scenes for training or testing purposes because those have the ground truth. You know exactly where everything is and so forth. But collecting these scenes is very expensive. You can easily drive around and record video, but to get these scenes would require someone to go in and label, here are the objects and where they are and so forth. So we'd like to ideally generate realistic scenes automatically for training and testing. Why is this a difficult problem? Well, it's easy to generate scenes, but hard to generate meaningful ones. The scene space is quite large. If you imagine a single car, for example, you have a bunch of parameters, position, orientation, color, and so forth. If you have a complicated scene with a lot of objects, this adds up, you get a high-dimensional space. And furthermore, if you sampled that space at random, you would get meaningless scenes. If you position 12 cars at random on a road, some might intersect each other, some will be facing backwards, and so forth. Whereas generating realistic scenes requires complex geometric constraints. So for example, people typically drive in lanes. They may deviate in certain ways, but only some of the time, and so forth. So really what we need is a formal model of the environment that these systems are going to be operating in. And the question is, how can we encode that? In this project, we argue a natural way to do that is using a probabilistic programming language. So what does this look like? The idea is you can write a program in such a language. Our language is Scenic, which I'll talk about later. And this describes a set or distribution of possible environments for the system. And if you sample from that distribution, you get scenes, these high-level descriptions, which you can then put into a simulator to generate the actual data. So here, as I'll talk about later, we're using a video game to get images, but you could get LiDAR data or whatever sort of data you need, and then use that to test your system. Or if your system uses machine learning, you could use the same idea to generate training data, maybe to augment some gap in an existing training set that was obtained from real-world data. And if you discover a failure in the system, so here this one car is misclassified as 3 cars, you can take that single counterexample, use that to write new programs, generalizing it to try to identify what the root cause of the failure is and then retrain without overfitting to that particular failure. But for all of this to work, you need a language which makes it easy to encode a wide range of environment scenarios. And that's why we developed Scenic. So Scenic is an imperative, object-oriented probabilistic programming language defining distributions over scenes. So for example, here's a Scenic program we wrote describing bumper-to-bumper traffic. And these are images rendered from 4 different samples from that same program. So Scenic has a formal, precise semantics describing a probabilistic model that lets you encode the kind of vague scenarios like bumper-to-bumper traffic, make that precise, and then generate samples. And even a complicated scenario like this one, with a bunch of lanes of traffic and different cars, can be written quite concisely. It's only 20 lines of Scenic, because Scenic provides readable, concise syntax for common geometric relationships. And furthermore, that domain specificity enables specialized sampling techniques based on configuration spaces that I'll talk about a little bit later. But like a general-purpose probabilistic programming language, Scenic allows you to impose declarative hard and soft constraints. So it's easy to rule out, for example, 2 cars intersecting each other. So just to summarize what we've done in this project, we've developed this Scenic language and specialized algorithms for sampling from the distribution defined by a Scenic program. We've also developed this methodology for using PPLs to design and analyze perception systems, particularly systems based on machine learning. And the main case study we've looked at so far applied Scenic to an actual deep neural network used for autonomous driving. And as I'll show a bit later, we're able to improve its accuracy beyond what you can achieve with existing state-of-the-art synthetic data generation techniques. So let me just give you an overview of some of the related work we're drawing on here. On the probabilistic programming language side, the semantics of Scenic are that of a standard imperative PPL. So I won't go into that in any detail in the talk. Of course, we have a formal operational semantics in the paper if you're interested. Such languages have been used as generative models of graphics, for example, the quicksand and picture languages. The main differences in Scenic are, one, that our emphasis is on generation, not inference, although of course they're closely related, and more significantly, the domain specificity. As you'll see, we put a lot of work into trying to design the language to make it possible to concisely describe these complex environments and in a way that enables better sampling. There's also related work on the computer graphics and ML side. So on graphics, there's work on scene synthesis from examples or from grammars. And on the ML side, work in data augmentation and generation, like GANs. The main differences with Scenic are that you have more control. You're not just giving a set of examples. What the programming language really allows you is you can say, these features should remain fixed, these should vary in this prescribed way. So you have a lot total control versus just giving a set of examples. It's also easier to use than writing a grammar, we would argue, and you can interpret it. Unlike a GAN, where you have no idea what distribution it's coming up with, here you know exactly what the distribution is. So, as I said, there's a formal semantics of and syntax specified in the paper, but I'll just illustrate the language with an example. So say we want to encode this kind of scenario, a badly parked car. How can we do that? So on the left here, I'm showing kind of a schematic with the ego car where the camera is on the left, and the other car at the bottom, which is near the curb, but it's a bit off and at a funny angle. So how can we write that? So the first thing I'm going to do is import from a library everything specific to our car case study. So Scenic is not specific to autonomous cars, it just knows about geometry. So we wrote this library, GTA, for that video game that we're doing our case study in, that defines the class car, so this is a type of object, the curb, which is a region, that's another primitive data type in Scenic, here describing the red lines in the image, so where the curbs are in the simulated world. And the road direction is a vector field, that's another primitive type, defining at every point on the road what the nominal traffic direction is. All right, so now I can create the ego car. Notice I haven't said anything about where this car is located, what color it is, and so forth. So Scenic will use the prior distributions on all the properties of the car, which are defined in the class. So for example, the prior on a car's position we define to be uniform over the road, but probability 0 of being on the sidewalk, for example. All right, now I'm going to pick a parking spot for the badly parked car, and I'm going to do that in a few steps. The first thing I'm going to do is pass curb to this built-in function visible, which will restrict that red region to just the part that's in the view cone of the ego car. And now I'm going to pick a random point in that region. I'm saying create an oriented point, so this is a built-in class in Scenic, that is on, which means uniformly at random on that region. So on is what we call a specifier, which I'll come back to a little bit later, but basically this instantiates an instance of that class oriented point. All right? And it's oriented because it has a local coordinate system aligned with the curb. We'll see why that's useful in just a second. So now I'm going to pick an angle for the car to be parked at. And the way I'm going to do that is by sampling an angle uniformly at random between 10 and 20 degrees. So this interval notation means uniformly at random over that interval, times 1 or -1, so to the left or to the right. And now I can actually start creating the car. So I'm saying create a car to the left of that parking spot offset by ½ meter to the left. So this is like the Smalltalk vector syntax. It means ½ meter in the negative x direction. And I'm offsetting the spot by that. And because spot has its own coordinate system associated with this, this really means ½ meter into the road as compared to ½ meter west in the global coordinate system, which would not be what we want. And notice, in order to position the car ½ meter from the curb, I actually want its right edge to be ½ meter away, which requires knowing how wide the car is. So Scenic here will work out, it actually has to sample the width of the car in order to evaluate this expression. We'll come back to that in just a second. Finally, I want the car to be facing that funny angle, but again, not in the global coordinate system, relative to the direction of the road. So I can use this relative to operator there. So this is a complete Scenic program. Notice I haven't written down any constraints, declarative constraints, but Scenic has some built in. So in particular, Scenic will automatically guarantee that no two objects intersect each other. So if we sample from this program, we get scenes, which we can then import into the simulator to get images. And this is the kind of thing you get. So indeed, there's a car by the side of the road, but at a funny angle. But we left a lot of things unspecified, like the distance to the car, the time of day, and so forth. So we get quite a diversity of scenes that still match this high-level idea of a badly parked car. All right. So the most interesting thing about the language from a design perspective is what we call specifiers. So these are syntactic elements that define properties of an object, which you can combine to build up a complete definition. So for example, in this line of Scenic, the at is a specifier for the position property, and facing toward is a specifier for the heading property. And the reason we factor object construction into these independent parts is, one, that it gives you a great deal of flexibility. So Scenic has 9 completely unrelated position specifiers that mirror ways in natural language that you talk about position. So you can say something is at a particular position, it's ahead of something else by some distance, it's along the line of sight from some other object by a certain distance, and so forth. So Scenic has a whole bunch of these, and by having separate specifiers for them, we don't have to have a separate constructor or factory function for all possible combinations of specifying position and heading and color and so forth. But they're not just syntactic sugar, because these specifiers also capture dependencies. They can depend on other properties and other specifiers. So we saw this example before of the left of specifier, which determines the position of an object given its width. So you need to know the width first. Here's a more interesting example. The facing specifier specifies the heading property, and it doesn't normally have any dependencies. But this expression, 30 degrees relative to the road direction, that doesn't define a unique orientation. At every point on the road, that could define a different orientation. So here, Scenic tracks that that depends on the position property, and so this whole expression specifies the heading given the position. And internally, Scenic constructs a dependency graph to determine what order everything needs to be sampled in to generate the object, or report an error if there's a cyclic dependency or something. So just to give you an idea of how we do sampling, the basic idea is to prune infeasible parts of the space by dilating polygons, since we know we're talking about geometry. So for example, if you have a Scenic program with these 2 requirements, saying there's a taxi whose distance is within 5 meters, and its relative orientation compared to us is between 15 and 45 degrees, so it's at a bit of an angle. For example, you want an image of a taxi that's starting to turn or merge into a different lane. If we say that the taxi is roughly aligned with the lanes, then it's only possible to satisfy this near intersections, essentially. And Scenic can work that out automatically. So here's a map of part of Berkeley that we used in one of our experiments, and the red is showing all the roads, and here Scenic is able to prune away almost all of the space. Only the blue parts are left as feasible locations to position the car. So what can you actually do with the language? An obvious application is just to explore the performance of your system under different conditions. So you can write a scenario for a particular type of scenario or a particular type of situation and see how well the system works. So just to show you it's not all about autonomous cars, here's an example we did of testing a motion planner for a robot. So generating this kind of cluttered scenario where the rover is trying to get to the flag, and there's this bottleneck that forces it to consider crawling over those rocks. A more interesting application is debugging a known failure. So if we have this misclassification I showed before, where one car is labeled as 3 cars, we can generalize this in different directions. So varying the model of the car, the position, and so forth, converge on what the root cause of the failure is, write a more general scenario for retraining, and then get rid of the bug without overfitting to this particular misclassification. We were able to do that in this case. I can talk about it in the questions if people are interested. The application I'll talk a little bit about is designing more effective training sets by training on hard cases. So for car detection, for example, an obvious hard case is where one car is occluding your view of another car. So we can write a Scenic program generating that type of scene. So here's a bunch that are sampled from that Scenic program, which is just a few lines. And then use that to emphasize the representation of these type of images in the training set. So we did an experiment where we took an existing data set from that same video game that was obtained by just driving around at random and taking screenshots periodically. If you train on that data, this X matrix data set, and test on the same kind of data, you get some numbers. The absolute values don't matter. The point is, if you test that network on our overlapping images, the precision is significantly worse because the network intuitively has trouble localizing this car, which is in the back. So then what we did is we trained a new model with the same amount of data, same amount of computation needed, but now we replaced 5% of the training set with our overlapping images. As you would expect, the performance on the overlapping images goes up. The important thing is that performance on the original data distribution remains the same. So you can improve performance in this hard case without hurting the typical case by using a more intelligently designed training set. And Scenic gives you the ability to specify exactly what distribution you want your training set to have. All right, so just to summarize, Scenic is a domain-specific probabilistic programming language for describing scenes, which is useful for the design, testing, and debugging of cyber-physical systems, things like self-driving cars. And in fact, we have integrated it as the modeling language for Verify, which is a toolkit our group has developed for formal design and verification of AI-based systems, which will appear at CAV in a few weeks. And our implementation of Scenic is also online, so please try it out and let us know if you have questions, comments, feedback. Going forward, there are a few directions we're interested in and we're actively working on. One is other application domains. So for example, aircraft navigation. We have an interface to a flight simulator for generating different runway layouts and obstacles and things like that. Also interesting would be learning Scenic programs from data. And finally, encoding dynamic scenarios. So the case study I showed here was for testing a perception system. But if you want to test a controller, like the full system of the self-driving car, perception and control, then you'd like to be able to encode scenarios where things are changing over time. And we've done some experiments along those lines. So for instance, here's a simulation using Scenic of a crash, an Uber crash, where a human was turning left in a kind of blind intersection and they collided. And you can use Scenic to generate variations on this and do a sensitivity analysis and so forth. Oops. All right. So that's pretty much it. Thanks very much.
We have time for questions? Please come to the mic.
Yeah. Nice work. I had a question on the. So one of the problems is like this rare event simulation.
Right.
Like when so they train the systems, and like after some point on the common scenarios it works well.
Right.
But it's like finding this rare weird event. Like I guess it would be a Scenic description, which leads to a violation, like a crash or something. Right.
Right.
So how do you have some thoughts how to kind of integrate this rare event finding systems with Scenic?
Yeah, so basically the essence, if I understand correctly, was Scenic gives you the expressivity to describe interesting scenarios, but how do you find these difficult scenarios in the first place where the system might fail, right? If you write a generic kind of scenario, it might be the probability that you get to one of these failures is very low, right? So here we were focused mainly on giving the programmer the ability to define these scenarios, but of course it's a separate question of how do you come up with them in the first place. So this Verify toolkit, which I mentioned, has several strategies actually for actively searching for those. So essentially, you can think of Scenic as putting a distribution over this high-level feature space of describing the positions, orientations, and so forth. You don't have to search that space randomly. You could use optimization or other types of techniques to look through that space, and that is something we have in the Verify toolkit, and we're very much interested in integrating more into the language. Yeah.
And just like a quick follow-up. So like, how to use the probabilities, like the distribution? Like you would expect to have like an assertion at the end or something where you say with this probability the assertion holds based on your input distribution, right?
Right.
Like you didn't explain like how do you actually use the fact that you have a distribution?
I see, yeah. So here, the language, as I described it, was just for modeling the environment. But of course, you'd like to also monitor properties over the actual system to check like whether it fails or not, right? So in this Verify toolkit that I mentioned, essentially it combines this with runtime monitoring, where you can write down formulas like in temporal logic, say, to monitor the property of the car, staying on the road or not colliding and so forth. And so then you can do basically a search through the environment space to try to find falsifying scenarios where that property is violated.
All right, thank you.
Hi. I had a question about the keywords in your language, or
Right.
kind of the operators, I guess, for describing relative information. You have
Yeah.
9 of them. Is there a way to extend that, or what if I wanted to make my own?
Oh yeah, so right now it is kind of fixed. Like the set of specifiers I mentioned for positions, we just built them in. You can define your own, so I didn't mention, but the language is not embedded, but essentially implemented by translation to Python. And so you could define your own specifiers using Python, but you'd have to change our parser to recognize them and so forth. But allowing the user to define their own specifiers is something that we would like to do in the future. Yeah.
Last question.
Dietrich from Cornell. I had a question about, it seems like the language is built heavily around working with geometry and
Right.
especially uniform distributions.
Yes.
So I'm wondering how these properties might extend to, let's say I want to have multiple different car models that you mentioned at the beginning.
Right.
How do you have these sort of discrete objects?
Oh, right. So basically, Scenic doesn't worry about the exact details of the objects, for example. It just has this very high-level abstraction, essentially just bounding boxes. So if you want to, in like this case study we did in GTA, we basically wrote a Scenic library defining, saying these are all the different models of cars the simulator supports, here are their dimensions and so forth. If you had a simulator that allowed you to modify the meshes of the cars and things, you could also put distributions on those in Scenic. But essentially, Scenic just deals with the high level, and then you have to write a little layer hooking it up to the particular simulator. So in this case, we used a fixed set of car models. I mean, on the point you asked about distributions, the examples I showed only used uniform distributions, but you can also define non-uniform distributions. So for instance, in our case study, we used a non-uniform distribution over car color, which was actually learned from real-world car color data. So certain colors are more common. And Scenic, although I just showed the syntax for uniform distributions, of course supports arbitrary discrete distributions and other types of things.
Okay. Thanks.
Thanks.